Hi everyone, welcome back to Mathematics 0110. This is the second video on the introductory material for week 1. Something that's going to come up at different points in the course is the variety of ways that we can describe an interval or set of numbers. Probably the most intuitive way of representing a set of numbers is with a picture. Let's say a picture of the number line. Say we wanted to represent all the numbers that go from -5 to +10. So we could do it in the following way. Go -5 and 10, and then we would have some choices. We would have to choose, do we want to include the endpoints? Do I want to include the -5 in my set of numbers? Maybe I do, and I would shade it in. Or maybe I don't, and I wouldn't shade it in. What's shown here, if I shade in that particular point, and then shade in the region of the number line in between -5 and 10, this picture indicates numbers like -4, +8, 0, 1/2, pi, and a whole bunch of other numbers. In fact, an infinite number of them. But this is not a very easy to write notation to describe a set of numbers. So there's a variety of alternative notations that we would use to describe sets of numbers like this. For example, there's something called a bracket notation. We'd put square brackets around a number that's included inside our region of the number line, inside our domain, and we'll put round brackets around parts of the number line, or around an endpoint that's not included inside that interval. So for example, the interval that's shown here in this picture, I put a square bracket, -5, comma, 10, round bracket. That's how I would indicate all the numbers between -5 and 10 without having to draw that type of a messy picture. Another way of writing that same set of numbers is using an equality notation. So if this line represented x values, we would say that the numbers in this interval are all x values such that -5 less than or equal to x less than 10. So x is simultaneously larger than or equal to -5, so -5 is included, and it is less than 10. Not less than or equal to 10, but strictly less than 10. 10 is not included. This is called a mixed interval. It's called mixed because one endpoint is contained in the set of numbers, one endpoint is not contained in the set of numbers. Shown above this picture is the notation for a closed set of numbers. It's all the numbers between a and b, where a and b are included. We also have a interval that does not include either endpoint, so round brackets go around both of those numbers. And in the inequality, there's no equal signs underneath the alligators. Remember, the alligator always eats the bigger number. At least that's what they told us. And then there's the two mixed interval notations. All these notations are notations for a finite interval. So there's an infinite number of numbers in that interval, but you could get out a measuring tape or a meter stick and see how long the interval is. Or maybe a lot of meter sticks if it's a long interval. There's another type of interval called an infinite interval, where you couldn't measure how long it is. It also has an infinite number of numbers, and I won't say which infinity is larger, it's a discussion for a different class, but it does have a peculiar notational difference with the previous intervals that were just described. Anytime the endpoint is plus or minus infinity. So either time you can go as far to the right as you want, so you can go as high as you want in the numbers, or as far to the left as you want. You can go to very negative numbers. Then that plus or minus infinity gets surrounded by a round bracket. That's just the convention that we use. And the reason for that convention is infinity isn't really a number. We can't include it in as an endpoint because it isn't a point. It's more of a concept. It's the result of a limiting process. We will talk about limits and wrestle with infinity a bit, but we will end the course with infinity still kind of existing in this mysterious place. Anyway, so if we want to describe the set of numbers that go from a to infinity, where a is included, we would say square bracket a comma infinity, and then put a round bracket at the end of the infinity. That's our notation to indicate all the numbers larger than or equal to a, as big as we want. We make them as large as we want. There's no ceiling. There's no maximum. It's limitless. If we don't want to include the end point, or the beginning point, I guess, we put a round bracket around the a. And then there's a similar notation for negative infinity, whether or not the right endpoint is included. And these also follow the same definition of being open or closed. Open intervals are ones that include the that do not include any endpoints, and closed intervals in this case, if one of the endpoints is infinity, it's a closed interval if the other endpoint is included. So this is going to come up in different spots. It's going to come up when we talk about max and min at the end of the course, and it's going to come up at the beginning of the course when we talk about domain. Probably the most important piece of background mathematics for Math 0110 and for a lot of calculus-based math courses is exponent laws. The laws of exponents are a type of shorthand. Instead of saying I want to multiply 5 by itself 10 times and writing that as 5 times 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 5, I think that's 10 of them, but it gets super messy. Instead of writing 5 multiplied by itself 10 times, we would write 5 to the power of 10. It's just a shorthand for that. So a to the n, it really means a times a times a times a n times for whatever n is. That's at least the interpretation that we can use if n is a positive integer. If n is a negative integer, or if n is a fraction, then we have to use a different type of interpretation that's related to this. With a concrete example, 2 to the power of 6 is telling us we have to multiply 2 by itself 6 times. So 2 times 2 gives you 4. So that's 2 of them. Times 2 again, 8. Times 2 again, 16. Times 2 again, 32. We're not quite done yet. We got one more left, 64. Based on this definition, we have to accept that a number to the power of 0 is 1. You can treat this as a definition if you want, but it's actually necessary for other reasons. That a constant to the power of 0 equals 1. Or actually anything to the power of 0 is equal to 1. Does that be a constant, be a function, with one exception. 0 to the power of 0 is undefined. If you read somewhere that it's equal to 0, they're wrong. If you read somewhere else that's equal to 1, it's also wrong. It's equal to neither. So some examples are given on the right hand side. Some of them are normal, like 6 to the 0, and some of them are abnormal, like 21 over negative 2 pi all to the 0. What all those things in brackets have in common is that they're all just numbers. Even though if they were functions, they'd be 0 everywhere except where the function is equal to 0. Or they'd be equal to 1 everywhere except the function is equal to 0. Now, what happens if a is not a positive integer? What if n is not a positive integer? What if we have a to a negative power? We would interpret a to a negative power as 1 over a to the positive of that power. So as an example, 3 to the power of negative 2, we would interpret that as 1 over 3 to the power of positive 2. Then we can simplify that. 3 to the power of positive 2 means 3 times 3, which is 9. 4 to the power of negative 3 is not negative 12 or positive 1. It's 1 over 4 to the positive 3. Every time we see that negative power, we have to keep in mind that it is telling us that the expression is actually in the denominator. It's just a shorthand for that, so we don't have to write the fraction. But if we're going to do anything with it, now we've got to introduce the fraction and then use the exponent laws. So it's really just to keep it compact temporarily. Anyway, 4 to the negative 3 becomes 1 over 4 to the positive 3, which means we multiply 4 by itself 3 times in the denominator. 4 times 4, 16. Now multiply by 4 again, 64. All right, well that's negatives. What about fractions? If you have a to the power of 1 over n, so that's one type of fraction, where the numerator is 1, the denominator is any integer, then that can be interpreted as the nth root of a. So some examples are given. 27 to the 1/3 means cube root of a, which is asking us which number multiplied by itself 3 times gives you 27. Which number multiplied by itself 3 times gives you 27, and the answer is 3. 3 times 3 times 3. 16 to the 1/2 means square root of 16, and that's asking you what number multiplied by itself twice gives you 16, and the answer is 4. And then the last type of power that you can have is, well, I shouldn't say it's the last type, but another type of power that you can have is a fractional power where the numerator is not 1. In this case, the numerator is indicated by the letter m. So we have a to the power of m over n. This has to be interpreted in 2 ways. First, the m is telling you to multiply that base by itself that many times. And then the n in the denominator is telling you to take the nth root of that result. Now you can also do those operations in reverse. You can take the nth root first and then take that result and raise that to the power of m. So some examples or one example in different ways is shown here. 8 to the power of 2/3. You can interpret this as first squaring the 8 and then taking the cube root of that result. So 8 squared is 64. Now what's the cube root of 64? Well, that's asking what number do you multiply by itself 3 times to get 64, and the answer is 4. Or you can interpret it as take the cube root of 8 and then square it. Cube root of 8, what number multiplied by itself 3 times gives you 8? The answer is 2. Now 2 to the power of 2, you get 4. Notice that both approaches give you the same final result. Which one's better? I think in this case the second one is better, because taking a root of a number like 8 produces a smaller number. And then you square that smaller number. Whereas if you start by squaring the 8, now you've made a larger number, harder to work with. Now you're taking the cube root of that. So the order of operations for fractional powers, they're both going to result in the same outcome, but I think sometimes one way is better, and that's to use the root first. So that was just notation of exponents. It's what does this shorthand mean? What comes next are the laws of exponents. The laws of exponents are a type of accounting of multiplication. I'm going to go through not really a proof, but an explanation for each of them. First one, a to the m times a to the n is a to the m plus n. You probably memorized this in other math courses, but I want to explain why it is that way. I'm going to do that with an example. Say we have 3 to the power of 2 multiplied by 3 to the power of 3. What does that mean? Well, that means we have 3 times 3, well that's the 3 squared, times 3 times 3 times 3. That's the 3 cubed. Now, how many times do we have 3 multiplied by itself? We have multiplied 5 times. So we could rewrite that as 3 to the power of 5. That's why the exponents add. It's just keeping track of how many do we have. So some examples are given on the right, or one example is given on the right, which with x's in it, but it's the same idea. 2x to the 3 times 5x to the power of 4. We don't use exponent laws in the 2 and the 5. There's no power on those. We can just multiply them together, so 10. But we do need exponent laws for the x part, the x to the 3 times x to the power of 4. So that's x to the power of 3 plus 4, which is x to the power of 7, not x to the power of 12. The next law of exponents is related. It's for division. A to the m over a to the n equals a to the m minus n. Why? Well, concrete example. I'll pick on 3 again. Let's go 3 to the power of 8 divided by 3 to the power of 4. You look at this and you say, is the answer 3 to the 2? Do I divide the 8 and the 4? Or is the answer 3 to the 4? Do I subtract them? Or do I do something else? Well, what happens if you write it out? What is 3 to the 8? It's 3 times 3. I'm regretting choosing 8, but it's okay. That's 5, 6, 7, 8. And then 3 to the 4 is 3 times 3 times 3 times 3. There's the 4 threes. Now what can we do is cancel. Cancel, 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 cancel. What do we have left? Well, down below we have a 1. Up above we have 3 times 3 times 3 times 3 over 1, which is 3 to the power of 4, which is what we got by subtracting the powers. 3 to the power of 8 minus 4, not dividing the powers. And an example is given on the right hand side, this time without x's, but with fractional powers on a number. So you can simplify each one separately if you want, or you can subtract the powers and then simplify. Okay, the next exponent law is what happens if you have a power, so something to a power, and then you take that stuff and raise that to another power. What do you get? Let's do an experiment and make sure that this rule that shows that the powers multiply, and then you raise that base to those multiplied powers. Let's confirm that this is actually the case. I'll pick on the base of 3 again. Hope you don't think there's anything special about that. I'm going to do 3 to the 4, all to the 3. And we'll make sure that this is what is claimed, that this ends up being 3 to the power of 12. So let's confirm that. This is 3 to the 4 times 3 to the 4 times 3 to the 4. That's 3 to the power of 4, all cubed, all to the power of 3. So there's 3 of those things multiplied together. Now I'm going to take each of those and expand them, or not expand them, but rewrite them. So 3 times 3 times 3 times 3, that's the first 3 to the 4. 3 times 3 times 3 times 3, that's the second one. And then 3 times 3 times 3 times 3, that's the third one. How many do we have? We have 12 of them. So we can say this is 3 to the power of 12 as needed. Well, that's almost the same example. Okay, next rule. A times b to the n can be rewritten as a to the n times b to the n. This means if you have a product or a multiplication of two numbers, a times b, and those two numbers are together raised to that power, n, then you could obtain the same quantity by first raising a to that power, then raising b to that power, and multiplying those two things together. Let's check that by doing this. 2 times 3 to the power of 4 is 2 times 3. I know it's 6, but leave it alone. Trust me. Okay, so that's 2 multiplied by itself, or 2 times 3 multiplied by itself 4 times. Now I'm going to use a property that for numbers, if you're taking Math 1229, for scalars, a times b is equal to b times a. The order of multiplication does not matter. 5 times 4 is the same as 4 times 5. And I'm going to use that rule as many times as I need in order to reorder all the multiplications that are shown on the left. I'm going to put all the 2's together. I have the first 2, the second 2, the third 2, and the fourth 2. And then I'm going to put all the 3's together. 3, 3, 3, 3. Well, that first bracket is 2 to the power 4. And the second bracket is 3 to the power 4. So that shows that the property holds. The last one is the same. Instead of having a times b, it's a divided by b. And I think you can set up like the example I just did. Instead of 2 times 3, do 2 divided by 3, all to the power of 4, and then multiply top times top times top, bottom times bottom times bottom, and the rule will fall out. Okay. These are going to come up often. We're going to be doing a lot of stuff with exponents and exponent laws. Some of the language we'll use in this course is around mathematics you may have seen in grade 9, grade 10, and hopefully reviewed in grade 11 and grade 12 if you took a grade 12 math course. So I'm going to review some of that terminology. One piece of terminology is the polynomial related terminology. A term like 2x to the power of 3 is called a monomial. It's one piece. It has a coefficient in front. The coefficient could be positive, it could be negative, it could be a whole number like 2, it could be a fraction like 1/2. And it has x raised to a power. X to the power of 0 would count as a monomial term. So 2x to the power of 0, 3x to the power of 0, that's just 2 or 3 respectively. So a constant can count as a monomial. Now, one thing that we need in order for this to qualify as a monomial is that the power must be a whole number. And it has a positive whole number. So 0, 1, 2, or positive or 0 whole number. So 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, and so on. Can't be negative, can't be a fraction. So that's the power on top of the x. To qualify as a monomial. If we take a bunch of these monomial terms and string them together, that's called a polynomial. Poly meaning many. So many monomials. Some examples of polynomials are given on the slide. When we work with polynomials, and when we work with all function types, we have certain rules that we need to follow. And the rules are followed so that we have a consistent mathematical language. That the answer that I get is going to be the same as the answer that you get. One set of such rules, like exponent laws, or exponent rules, is BEDMAS, or PEDMAS, or whatever acronym you used. That tells you the order in which we're supposed to complete operations like multiplication, division, addition, and subtraction, and also exponentiation, logging, and other things. Now, logs aren't part of that, but it follows the same rules as exponentiation. Anyway, this tells us to do what's inside brackets first, then to look at exponentiation, then to look at division, multiplication, and then to look at addition and subtraction. Another thing connected to polynomials when you first learn it, but actually extensible to other types of functions aside from polynomials, is FOIL. So how do you expand an expression? If you have two brackets multiplied together, how do you expand it out? Well, if the two brackets each contain only two terms, the FOIL acronym completely describes the process you would follow. You multiply the first times the first. So for the example shown here, 7x times x to the power of 3. That's the f part. Then there's the outside part, outside times outside, the 7x times the 3x. Then there's the inside, the 2 times the x cubed. And then there's the L, the last, so the 2 times the 3x. And we can simplify. 7x times x to the power of 3 is 7x to the power of 4 using the laws of exponents. So there's an x to the power of 1. There's no power on x. We can always assume there's a 1 there. X to the 1 times x to the 3 is x to the 1 plus 3, which is 4, plus 7 times 3, 21. X to the 1 times x to the 1 is x to the power of 2, plus 2x to the 3 plus 6x. We would next look for like terms, and we don't have any. Each of these monomial pieces have different powers of x on them, so they can't be combined. We could common factor an x out if we wanted, but it's not asked of us. All the question says is example, and above it says expanding, so I think we're supposed to expand. So we did that. Well, we didn't have class on Monday, did we? Our classes are Mondays and Wednesdays, and the other section, they're Wednesdays and Fridays, so I really have to not I have to get out of this habit of putting stuff like that. So factoring was in the other note. In lesson 1A, we went through different types of common factoring and factoring of quadratics. Factoring quadratics using a product and sum method, and factoring quadratics using difference of squares method, if applicable. You also learned inside that video how to check your answer. Once in a while, when you're doing your homework, you'll come across a problem that requires the quadratic formula to fully factor. And I believe it happens at the end of the course when everyone's going to forget this was in here. You're not going to be asked to use the quadratic formula on a test or a quiz or an exam. It may come up. It may come up at a few spots in the homework. Let's see. But I think that's it. And in future math courses, it will come up. What it is a general form for factoring an expression, a quadratic expression, ax squared plus bx plus c. And often we do that factoring for setting a quadratic equal to 0 and finding the roots. So if you want an expression just for those roots, just for the x values that makes that quadratic equal to 0, or those solutions are going to be given by this magic formula. X is equal to the negative of b, whatever b is, plus or minus the square root of b squared minus 4ac, all over 2a. Now, this will give you two solutions if b squared minus 4ac is not 0 and not negative. If b squared minus 4ac, which is called a discriminant, if it's negative, you're not going to get any solutions. If it's 0, you're only going to get one solution. Oftentimes when factoring quadratics or setting a quadratic equal to 0, it's a good practice to calculate b squared minus 4ac to check if there's even a real answer, a real solution. If you plug the numbers in, a, b, and c, into b squared minus 4ac, let's say you get negative 10, that means you don't look any further. You don't look for the product and sum method. You just say there's no solution at all. An example I don't want to go through, you can go through on your own on the slide, is given here. 3x squared minus 10x plus 5 is equal to 0. Product and sum method won't work. You can try as long as you want. You'll just waste paper. And if you plug those numbers in, this is why the product and sum method won't work, because you're not going to guess the answers are 10 plus root 40 over 6 and 10 minus root 40 over 6. It's possible to simplify these. You can write root 40 as root 4 times 10, so the 4 and the 10 inside a root. Then you can write that as root 4 times root 10, which is 2 root 10. And then you can common factor a 2 from the top and cancel the two top and bottom. So there's lots of things you can do to simplify this further, but I'm not going to bother because you're not going to have to use this inside this course. And there's just a note about the discriminant. Probably being the only important thing to take away from the slide is when you think something factors and it's not working out, make sure that this discriminant b squared minus 4ac isn't negative. Because if it is, you're just wasting time. You're not going to find a root. You're not going to find a way to factor that quadratic. Right, the next piece is on rational expressions. So functions or expressions involving a fraction. These could be numbers, like 7 over 3, or they could be expressions involving variables like x and y. Sorry, I gotta take a step back. For a rational expression or for a rational function, the top and bottom must be polynomials. So that's for rational functions. We often do subtraction, multiplication, and division of rational expressions. And there's certain rules that we have to operate with in order to complete those. When you, for example, multiply two fractions together, whether they involve x or not, to multiply, we would do top times top and bottom times bottom. So some examples are given on the right-hand side. Division is a little more interesting. How do you divide by a fraction? It kind of hurts the brain, I think, to imagine this, but how do you take 1/2? Let's first just divide by 2. You have half a pizza and you want to divide it by 2. You know what the answer is. You know you're going to get a quarter of a pizza, but I'll say 1/2. And then what you're supposed to do to make sense of this algebraically is replace the division by a multiplication. But you're not going to multiply by 2, you're going to multiply by the reciprocal. You're going to take the 2 and flip it up and down. But there's no down, there's no denominator. Well, remember, if there's no denominator, there can always be a 1. So I'm going to take that and rewrite it as a 1/2. So I flip the 2, it's a 1/2. Now I'm going to use that first rule, top times top, bottom times bottom. I get 1/4, I get 1/4 of the pizza. So that's taking a half and dividing it into 2. What happens if I take a half and not divide it by 2, not divide it by 4, but divide it by 1/4? What are we doing? Well, let's just follow the algebra. Let's follow what the process says. I'm going to take my division and change the multiplication and then flip top and bottom. So multiplication, and instead of 1/4, it's now 4/1. Top times top, 4. Bottom times bottom, 2. We get 2. So 1/2 divided by 1/4 is 2, not 1/8. 1/2 divided by 4 would give you 1/8. Confusing, I know. Just follow the algebra. Don't try to think about it. For addition of fractions, this is the one people tend to remember the most. It's just make common denominators. Make sure that they're measuring a quantity out of the same proportion. Like you've got a half a pizza and a third of pizza, and you want to find how much that is. Measure them both out of how many sixths of a pizza. So let's say, make it more interesting. We'll say it's 5/6 of a pizza. No, not 5/6. What am I saying? Too high. 2/3 of a pizza plus 1/2 of a pizza. How much pizza is that? I don't know. I have to cut the slices up. So in the pizza that's been cut into thirds, what I'm going to do is I'm going to take each of those thirds and cut them into halves. So how many sixths am I going to have? I'm going to have 4. So I cut those 2 pieces each into 2 more pieces. And then the 1/2 pizza, I'm going to cut each of those 2 pieces into 3 pieces. So 1 times 3, and then 2 times 3. So this is 7/6. So I got a whole pizza plus 1 slice, which is, and that slice is 1/6 of the pizza. And the operations all work the same as you saw in the first video. If this fraction involves x, we do the exact same thing. We make common denominators, multiply top and bottom of one expression, of one of the fractions, by the bottom of the other one. For subtraction, it's the same, except once we get common denominators, we just subtract top minus top, instead of adding top plus top. We'll be doing a lot of work with these types of expressions. Right, and the last thing is radicals. Just a review of how to work with radicals. I'm combining radicals with fraction rules, just to make it a little more complicated. And you have some homework that looks like this, so it's worth doing. We have x over root x minus 2 root x. I'm going to start by putting a 1 underneath the 2 root x, and then make common denominators. So that x over root x, what I'm going to do to that is I'm going to multiply top and bottom by 1, the denominator of the other term. It's a very nice 1. Root x times 1. And then for the second piece, the 2 root x, I'll multiply over 1. I'm going to multiply top and bottom by the bottom of the first piece. So multiply by root x and divide by root x. And we can simplify. I have top times top, so x over root x minus 2 root x times root x over root x. Now we have to use another rule that we've already learned about inside this video, but in a way that we haven't used it yet. That's square root of x equals x to the power of 1/2. So square root of x times the square root of x equals x to the 1/2 times x to the 1/2. And we already learned that the laws of exponents require that if we have x to a power times x to the power is at. So x to the 1/2 plus 1/2, we get x to the power of 1. So we can say that root x times x is just x, which is going to work for x larger than 0. Okay, so I have x minus 2x all over root x. They have a common denominator, so I can subtract them. Now we can combine like terms. I have 1x minus 2x, so I have negative x over root x. I'm going to circle that as the answer. Then I put a little or here. See how it says that root x times root x is x? I'm going to use that in reverse now. So this x I'm going to replace by root x times root x. And then notice we can cancel the root x top and bottom. So it's also equal to negative root x. I'm mentioning this because the textbook loves to do this, even though it's no longer necessary. It's kind of it's an artifact of the past that we do what's called this rationalizing for square roots. You're not expected to do that. All right, last question here. We have 4x over root x plus 1 plus x times root of x plus 1. We're going to do the same thing. I'm going to put a 1 underneath and then make common denominators. So 4x over the square root of x plus 1 times 1 over 1, multiplied by the bottom of the second fraction, and then plus x times the root of x plus 1 over 1, multiplied by top and bottom by the bottom of the first fraction, root x plus 1 over root x plus 1. I'm going to use the rule that was previously established up above, that root x times root x is equal to x, but I'll generalize it, that root a times root a equals a, from the laws of exponents. So we have 4x over the square root of x plus 1 plus x times x plus 1 over the square root of x plus 1. Since root x plus 1 has root x plus 1 is just x plus 1. Now we can combine the numerators together, 4x plus x squared plus x. I'll expand that bracket as well. And now we can combine like terms and reorder the terms, putting the highest power of x first. So x squared plus 4x plus 1x is 5x over the square root of x plus 1. You can do something similar to this. You can rationalize this, but please don't. It's not expected that you're going to rationalize your answers. There you have it. So that's it for this week. Do the review, which consists of the Chapter 0 homework, 0.3, 0.4, 0.5, I think. The functions bootcamp. And then if you haven't already done it, the math readiness assessment that's on OWL. See you next week.